Hello everyone and welcome to another Pat Problems video. I'm Helena and I'm the Access and Outreach Manager for the Department of Materials at the University of Oxford, and today we're going to be taking a look at question number 21 from the 2016 Pat paper. So let's have a look at this question. So this is an optics question. So here we're told we have a sphere of radius r equals 2 meters made of a material with the same refractive index as vacuum. So that is a refractive index of n equals 1. And this is supported within a fluid with refractive index n by a straight wire going through its centre C. Okay, so let's look at the diagram. We have our sphere here, surrounded by a fluid and supported by this wire going through its centre here, which is this line. A laser is directed towards the sphere with its beam parallel to the wire but offset by 1 meter. Okay, so this arrow here is our laser pointing at the sphere, and it strikes the sphere at point A here. We're being asked what refractive index n would be needed for the refracted beam to travel at 45 degrees relative to the line AC, so the line between A and C, which includes both points. Okay, so let's just have a closer look at our diagram and see what we've got going on here. So we have our laser approaching the edge of the sphere here. Now, if we think about refractive indices and lasers refracting at a surface boundary, the equation that we think of is Snell's law. So we're thinking about the incident angle and the refracted angle and the refractive indices of the two mediums that we're using. So in order to set that up, let's think about the angles that we have going on here. So this laser is being shone at the surface. So let's draw a tangent to the surface sort of faintly here so we can imagine it as some nice straight lines. And we also need to think about the normal to that surface. And that is actually the same as the line AC here because that is a radius. That's the radius of the circle. So the radius will be at a normal to tangents of the circle edge. So we have our normal line here, which means that this angle here is our θ1, and it's going to refract some angle like this. So we have our θ2 here. Let's think about the refractive indices as well. We have our refractive indices here, n1, which we're told is n. That's what we're being asked to find. And our n2 is equal to 1 here with the sphere. Okay. So we have two unknown angles. Can we figure out what one of the angles is? Well, yes, we can actually figure out what this θ1, this incident angle, is looking at the geometry of the setup. So we can see here that this angle at the center here is the same as the angle there. We've got some sort of similar triangles going on. So we know that this angle here is also θ1. We know that this distance AC is 2, it's the radius. And we also know that this distance here is 1 meter. So using a bit of trig, we can calculate what θ1 is. So let's just draw this triangle out to one side so it's a little bit clearer. So we have θ1 here, we have a length of 1, and we have a length of 2 here. So using some simple trig identities, we know that sine of θ1 is equal to 1 over 2. That over that. And, I mean, you can put this in your calculator, but this is one of those that you should probably remember. That means that θ1 is equal to 30 degrees. So our incident angle there is 30 degrees. Okay, so let's think back to Snell's law here. We have n1 sine θ1 is equal to n2 sine θ2. Let's put in our values for all of these. So our n1 is n, that's what we're being asked to find. θ1 is 30 degrees. n2 is 1. Sine θ2 is 45 degrees. So that's what we're told in the question. So θ2 is equal to 45 degrees here. And now let's calculate this. So again, these are identities that you should probably remember. Sine of 30 is a half. Sine of 45 degrees is 1 over root 2. So rearranging this, we have that n is equal to 1 over root 2 divided by a half, which is equal to 2 over root 2, which simplifies down to simply root 2. Always good to leave these in exact form unless the question asks you to leave it to a certain number of significant figures, which it doesn't. So I'm going to leave my answer here as root 2. So that is the answer to the first part of this question. That's the refractive index that we would need in order to have the setup that's asked for in the question. Okay. So the second part of this question, we have another beam, another laser, not necessarily parallel to the wire this time, strikes the sphere at the same point, at point A. We're being asked to find at what angle relative to this line AC, that normal line, should the beam be directed such that it would be completely reflected by the sphere. Okay, so let's think physically what we've going on here. So in this sort of setup, where we've got this laser incident on the sphere, this change of refractive index between two different mediums, we have refraction, but we'll also find that some light is reflected. So we're being asked to find what the condition is for all of that light to be reflected. So we've got no refraction here. And that would be the critical angle. This would be the critical angle for which theta 2 is 90 degrees. So we have all of the light going across here or being reflected. Okay, so for this scenario, we want that theta 2 is equal to 90 degrees. So let's set up our Snell's law again. So we have n1 sine theta 1. I'm going to write it out again just for completeness. It's sine theta 2. In this case, we have theta 2 is 90 degrees. Our n1 is equal to root 2, which we've calculated in the previous question. And our n2 is still equal to 1. And we want to find what theta 1 is. So let's put those values in to our calculation. So our n1 is root 2 times sine theta 1 is equal to 1 times sine of 90 degrees. Well, sine of 90 is 1. So we have that sine of theta 1 is equal to 1 over root 2, which again, we could put that into our calculators, but hopefully that's one that you remember. So that gives us that theta 1 is equal to 45 degrees. So that's the critical angle at which the light would begin to just totally be reflected. So for any incident angle greater than this, we would have reflection. So our answer is actually that theta 1 must be greater than or equal to this angle so that we get all of the light reflected and none of it is refracted into the sphere. Okay, so that is the answer to this particular question. As you can see, it sort of had two parts to it. If we're thinking about the current format of the PAT where it's multiple choice, this could easily be split into those two parts. So looking at the mark scheme for this first part here was worth 4 marks, and then this second part was worth 2. So you might see that split up in a similar way. So it's sort of 2 smaller part questions that are multiple choice. Could even be split further into 3 2-mark questions. But that's how I would potentially split up this question to make it fit the multiple choice format currently used by the PAT. But at any rate, hopefully this is a good question, some good optics practice, bit of Snell's law, and hopefully that was useful for you to see my way of solving this. And please do join us again for more PAT problems videos.